Street Physics. All right, let's do some of these magnetism problems. The first question we had was a lightweight glass sphere is hanging by a thread. Yeah, let me draw that sphere. All right, there's my lightweight sphere, and there's a, looks like a bar magnet is nearby. All right, and that's glass. Suppose the sphere is electrically neutral. All right, how does it respond? Strongly attracted to the magnet. No, there's no electrical charges involved, and there's no the glass doesn't exhibit any significant magnetism. Weakly attracted to the magnet. Nope. It does not respond. Yes, that's true. It does not respond. All right. So glass isn't magnetic, so it's not going to respond to a magnetic field, and therefore there's not going to be magnetic attraction, and since it's neutral, there's not going to be any sort of electrical attraction or repulsion either. So the answer is ay. Does not respond. So A is ay. B. How does a sphere respond if it is positively charged? Well, if this thing's positively charged, then as this gets nearby, this is going to polarize, right? This side's going to become negative, and that side positive, and they will attract. They will attract, right? So this, a charged object will attract a neutral object. I assume the bar magnet is neutral. But either way, it's metal. And you get an attraction there. An electrostatic attraction, not a magnetic attraction. So B was, I'll say it's weakly attracted to the magnet. Ay. It's weakly attracted to the magnet due to the charges. This would polarize and it would attract. A metal sphere is hung by a thread when the North Pole is brought. All right, so now we're a metal sphere. Get rid of that charge. A metal sphere hangs by a thread. It says metal now. When the North Pole of magnet is brought near, the sphere is strongly attracted to the magnet. Then the magnet is reversed and the South Pole is brought near it. How does the South sphere respond? Well, what's happening here is the reason we have this attraction, this magnetic attraction, is because this must be not just a metal, but it must be a ferrometal. It has iron in it probably, and it could be nickel or cobalt, but it couldn't be aluminum, otherwise there wouldn't be any magnetic attraction. Couldn't be copper, couldn't be brass, right? So this is attracted because the reason it attracts is because when this is in a magnetic field, right? What's going to happen is we got this magnetic field, right? Going out like that, right? And let's remind ourselves, what's the direction of the magnetic field lines here? I know they go like this, and you'd have some go like this. So these field lines are going through, and they could be on the other side too. I'm not going to draw them right now. So if I put that here, south is attracted to north, so therefore the field is this way, right? So there's basically a field going this way through there, and that will cause the domains in the ferromagnetic material. It's metal and it's attracted magnetically, so it's going to be ferromagnetic. That causes the domains to line up. So these domains would line up like that. You'd get all these little domains lining up inside there. The electron spins would align, and basically this would be, I'll use a different color. Should have drew it bigger. When I do it again next time, I'll make it bigger. South, north, right? So then that becomes a magnet, south, and then they attract. What was the question? So, and then when we flip it around, it attracts again. So let me draw it again. So now we flip that thing around. So that was north, and that was south, and it still attracted. What's going on there, right? We still had our field lines where we had, our field, I'll just make it nice and big, right? Looping around like that. And then, of course, we had on both sides. I guess I should always draw them on both sides. I'm not going to draw a whole bunch of them. You get the idea. I'm going to grab this again, make sure that I got my direction right. I'm going to grab my compass. I'm going to put it here. South is attracted to north, so the field is therefore that way. It's this way here. So, you think I would have learned my lesson by drawing that bigger after that one, but some of us just don't learn, right? All right, so what's going to happen, I'm going to go with a different color. I lost my pen cap. Here it is. So that's going to cause domains in here to line up like this. So we got a whole bunch of domains lining up like that. And so that is going to cause this to be the north pole of a magnet right here. And this would be a south pole of a magnet. And then they attract again, right? So, anyways, we call these metal sphere, this would be a soft magnetic material in that its domains can flip directions quite easily. It doesn't hold its magnetism really great, just a little bit like you saw some when I had the nail, and it held its magnetism a little bit, but it wasn't great. So it's going to flip easier than this. This is a harder magnetic material, and once you magnetize it in one direction, it tends to stay that way. Now you can thwack the magnetism out of it, as you saw in I don't know if I showed you that video yet. I have a video where I thwack the magnetism out of it. You can thwack the magnetism out of that by smashing it, but this tends to hold its magnetism better than that would, and this will flip its domains, and that metal sphere will attract regardless of what side you put it to. All right? So how does the sphere respond? It attracts in both ways. It attracts this way because it becomes a magnet with the south end near the bar magnet, and it attracts this way because it also, again, becomes a magnet only this time the north end is near the south end of the bar magnet. All right, the discovery of the magnetic field, a copper. All right, so I guess I need to draw this thing. All right, so we have a copper rod, copper right there. Now, copper is not magnetic. It doesn't exhibit any strong magnetic properties where it sits on the periodic table, and with its valence electrons and the way the spins are and everything, it gets into quantum mechanics and things like that. But this does not exhibit magnetic properties. Neither is this insulator going to. And the bar magnet will. And then we had, what is that? That's a wire. Current carrying wire is shown. And it looks like the wire is into the board. So we got a wire coming out, and it looks like the current is into the board using the arrow convention. All right, for each, will it stay where it is, move toward or away from the wire, rotate clockwise or counterclockwise? Explain. The neutral, now, all right, so, well, first thing I'm going to do is, this has current going in it, so there's a magnetic field created by that. So I'm going to draw that field. I think I'll draw it in red. Right? So it's going in. I'm going to use the right-hand rule for current in the wire, where I'm going to take my right hand, make sure you're using the right hand, and I'm going to grab the wire, and my thumb is going to point in the direction of the current, and my fingers will wrap in the direction of the field. So I go like that, and I see that the field is like this. Right? Going to look like that. There's our magnetic field. There's our magnetic field. That's a magnetic field line. Now, the magnetic field is actually a vector. At this point, the field is pointing this way, it's pointing that way. These are field lines that I'm drawing. We're going to get into the vector nature a little more in a bit. But anyways, there's the shape of the B field. Let's see. Well, copper is not going to, it's not going to do anything. It's not going to attract because the only way it would attract is if there was a net charge on this, and there isn't. It's just a copper wire with current traveling through it, so it's still neutral. This is neutral. Oh, our insulator has charge on it. I didn't see that. So let's draw some charges like that. It's polarized. It looks like it's neutral, but it's polarized. The polarized insulator. What's a polarized insulator going to do? There will be an attraction here because there will be a slight attraction due to the electrostatics because this is a positively charged object. I know the whole thing's neutral, but this is quite a bit farther away. So this thing sees a positively charged object. So this wire is going to become a little bit polarized too, and there is going to be a weak attraction. Probably not much to speak of, but there would be a weak attraction here, an electrical one. And so for A, nothing. Right? Nothing's going to happen. B, there'll be a weak attraction. Right? So I don't know if it's going to be enough to pull it towards it, but there will be a weak attraction. And C, let's see what's going to happen. Well, all right. So we got this. It looks like this, and what magnetic fields? Oh no! Right here we have a field like this, and this magnet is going to try to. It's like a compass. This is a compass, right? This is basically a compass, right? So, and I only drew one, but you know we have these field lines. You're going like this, right? So this is a compass. So what's my compass going to do? It's going to want to align with the magnetic field. So this is going to want to rotate this way. It's going to want to rotate this way, right? Until it gets like that. And then it would be very, 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 very happy at that point. Once it got to that way, it wants to align its magnetic field with the existing magnetic field. So this will rotate. That's not how you spell rotate at all. This will rotate, and it will rotate this way, which is, I guess, counterclockwise. It will rotate counterclockwise. It'll try to. I don't know if it's going to be a strong enough field. I don't know if it can spin easily enough, but that's what it's going to want to do. It's going to have a tendency to rotate counterclockwise. Depends how strong the magnet is. Depends how much current. All right, let's take a look at 7. For each current carrying wire shown, draw a compass needle in its equilibrium position at the dots. All right. So 7A. Let's take a look at 7A. I'll write that right here. 7A. And what do we have? We have a wire like that. And current is going into the board. Boink, that way. All right, yeah, so there we go. So we got a wire, and there's current going that way. And we had a point in space and a point in space here. And we want to know what's the direction the compass is going to point. Well, I'm going to draw my magnetic field. I'm going to draw my magnetic field lines around here. So current's going in like that. So looks like the field is doing something like that. That'll be the direction of the field. And therefore, my compass points in the direction of the field. So at this point, the compass is going to point that way. And this way, the compass is going to point that way, right? It's going to be like this and like that. That's what my compass needles are going to look like there. And then on the other one, we had current coming right at you. And we want to know, so here's the wire with current coming out. And we had some dots sort of like that. And I'm going to draw the field. It's going to be my first step, draw the field. All right, so that's going around like this. And I'm going to make sure my field goes right through those dots. Like that. There's our B, like that. And that means that this magnet, or that compass is pointed that way, and this compass is pointed that way. This is actually the direction at this point of the magnetic field. The magnetic field is in that direction. Boom. And the magnetic field here is in that direction. These are field lines, right, which are different than the vector fields. But anyways, there you go. The figure shows a wire directed into the page and a nearby compass needle. Is the wire's current going into, out of, explain. All right, so we got a wire and we have a compass that looks like this. And there's our north side. All right. Well, we know that it's going to form circular loops. The magnetic field around there is going to form loops, so let's draw that. It's going to go like this. And since this way's north, that's the direction of the field at that point. It's this way. And working backwards, if the field is like that, that means the current is coming out of the board. So the current is coming out of the board. It's coming at ya. You better duck, because it's coming at ya. The wire's current is coming out of the page, right? And I just explained it. Each figure shows a current carrying wire. Draw the magnetic field diagram. All right. All right. Well, we got a wire like this coming out. Boom. So the magnetic field lines are going to do something like this. Now the field drops off with distance. So with distance, they should get farther apart. I should have drawn it more symmetric, but you get the idea, right? They're closer together here because the field is stronger. The field is stronger the closer you get. It drops off with distance. And then here they should be farther apart. That shouldn't have got closer. That should have stayed the same distance. But I'm not going to take the time to draw that right. It would take too long. Take too long. I think I'll use my magnets. I think I'll use a real wire. All right. I'm using magnets while we're discovering, when we're learning about magnetism. See that? The circle is complete. All right, we got current going this way. Thumb like that. I'm going to go like that. So, boom! It's into the board on this side. And out of the board on the other side. Boom. There's one loop. There's boop, boop. So it's forming these loops. They're really like cylinders. And then if I want to draw another one, I got to space them out farther because the field is dropping off with distance. I wanted to get all fancy. And then if I was going to draw another row, I would make it farther apart than this because it's dropping off with distance. Magnetic field drops off rapidly with distance. It's not as simple as the electric field where it drops off with the distance squared because we don't have the wonderful symmetry we get like with spherical charges and stuff like that. But it does drop off rapidly with distance. It depends on the configuration of the magnetic field, how quickly it drops off. All right, so that was 13A and that was B. So there we go. Should look like that. Right hand rule, thumb points in the direction of the current, fingers wrap in the direction of the field. In the plane of the page, it's coming in on this side, coming out of the other. All right, for 14, we had wire kind of doing something like this. And we had the current going this way. I was going down like that. So I gotta get my hand all the way around here and go boom, boom. All right, so we have X's on this side and dots on this side. Yeah, so something like that. All right. X's on this side, dots on that side. Oh, 15, they mix it up. They're showing us the X's and dots. They're showing us the field, and we got to figure out what the current must be. All right. Let's rearrange my wire. All right. So on this one, we had X's on this side and dots on that side. So that tells me the field was going into the board on this side, out on that side. So curling around, I see the current must be going this way. The current that was causing this magnetic field was going that way. All right, so we had something like this. This was 1, this was 2. All right, so there we go. So, I kind of glossed over this because I didn't want to load you up with too much stuff because I've already loaded you up with a lot. There's a difference. We can express the magnetic field as a vector or with field lines. Field lines indicate the shape of the field, and the distance between the field lines indicates the strength of the field, and we can tell the direction from the arrows. A vector, on the other hand, we would, like if we wanted to know the magnetic field here, a vector would be in a specific direction, and it would be a straight line, and the length of the vector would indicate the strength at that point. So I'm going to draw the field line, and I think I'm going to use this. Let's see how this works out. I would like to have a nice circle here. So this is going to form a circle that goes around, and I'm gonna help myself out by, so the field lines is gonna go there, here. Because if I don't do this, I'm not gonna get a good circle. All right. So that's my circle. That'll be my guide for my circle. So my circle goes around like this. Right. All right. So there's my circle, and I erased my current direction. So for 1, it's into the board and it's going like this. This is what the field line looks like. Goes like that. And we're interested in the field at these 2 points. Right? So the B field vector, the vector is pointed tangent to this, so this has a field line that looks like this. That's what the magnetic field vector looks like there, and the magnetic field vector here. Looks like that. So that's due to 1. And 2 is in red. I should have made 2 in red. Let's do this. So here's 2. And it's also going to form circles. I'm going to draw the field lines again. A field line in blue. And so we got That's kind of going like that. And that's kind of going like that. So it's going to form a circular loop. Kind of like that. It's coming out of the board, so it's going like that. That's its direction. That's the field line for number 2. And in red, I'm going to draw the vector. So let's assume it's the same amount of current, I think. Yeah, equal currents. So the magnitude of the current's the same, so it's going to be about that long. So this field is going to be this way. That's terrible. That's terribly not straight. Oh man. So that's going to go something like that. There's our B field due to 1, and then in this direction it's going, at this point it's going this way, and there's our B due to 2. Alright, so we got these 2 fields. The black one is due to 1, and the red is due to 2. And then we want the net magnetic field. That was supposed to be in red. Got my colors all screwed. So what is the net magnetic field? I'll do that in blue, I guess. Alright, gonna use the parallelogram method to add up these vectors. So there's the net magnetic field due to both of them. Alright, so we see that we have a net magnetic field that way at these 2 points. Alright, so that was A. That was 16A. Alright. Well, if you were confused by 16A and you didn't know what to do, why don't you pause a moment and try 16B and then check this out. Or if you just messed this up for 16A, why don't you give 16B a try? Don't just watch the answer. That's not real helpful. And it's not real helpful. You got to work through this yourself. And that's how you learn. Alright, we had 1 and 2. Same drill. I'm going to draw a magnetic field line here that goes through here. And I'm going to draw the magnetic field line that goes through there. Draw my vectors, add them up. Alright. Let's go with blue for our magnetic field lines. Let's see if I can get super fancy and use the neodymiums. Yeah, it kind of holds it in place. I'm liking how this is working out. Let's see what we got here. So, my little makeshift compass. Something like that. Alright, kind of goes like that. And I don't care about up here so much, so I'm going to get a little sloppier. And this is coming out of the board, so it's going this way and that way. This has a magnetic field vector like that. And this has a magnetic field vector like that. Hopefully it's about the same size. And then for, oh, these neodymiums are strong. Let's take this, put it here. Just gotta go through that. Oh well. Close enough. Close enough, comes around, something like that. Alright, and again, it's coming out, so this way and that way. I'm going to go red on this. So this one is kind of like that. And this one is, oh, that's probably not great. It's kind of hard to draw a tangent when it didn't go through the dot. But anyways, It's at this point, it's kind of like that. B. Probably should be a little shorter. Boy, the red is inky. All right, so they will add up using the parallelogram method. There's the total B field. Something like that, right? So the B field at this point is going to be like straight down, and that one's going to be straight up. Equal in magnitude, though. They'd be equal in magnitude. So there you go. That was tricky. We had magnetic field lines, which are different than the vectors, the vectors. And for analysis and all that, really it's the vectors that are going to be important. We're not going to go dig too deep into the vectors, because magnetism gets complicated. So A, for each of the following, draw the magnetic force vector on the charge, or if appropriate, write F into the page, F out of the page, or F equals 0. All right, so they gave us a charged particle, they drew a velocity vector on it, and they drew the magnetic field. It looks like vectors there. They drew a vector space. Those are vectors they drew. All right, so first one, we got that. We got a velocity for A, and we have our B field is this way. B field is going that way. So I'm going to use the direction of the force equals QV cross B. Okay. So anyways, so I got V. Oh, my hand's not right because I can't bend them backwards. I'm going to have to, oh, still not right. Ah, that's right. V cross B into the page. So F is into the, I'm gonna go F, and I'm gonna put an X there. X is it. F's into the page. All right, B. We got our B field is down, and we have our velocity vector is also down. So you know. So V cross B, but B's in the same direction. V's in the same. I can't. There's no way to bend, right? I don't bend my fingers now because the same direction. The velocity vector's in the direction of the field. You know what that means. Okay, so the force on this, the magnetic force is 0. The velocity is in the direction of the magnetic field. There is no magnetic interaction with these two. All right. C, we had a B field going this way, and we had a negatively charged object with a velocity at right angles to that, like that. So I'm going to keep this up here. F equals QV cross B. So let's take our velocity vector. You make sure I'm using my right hand. The velocity vector V cross B into the board if it was positive, but it's not. It's not positive. It's negative. So this is F is out of board. F is out of the board. You know what I mean? So F is that way. I put a dot there. D. This was C. D. We had a field coming out of the page, like that, and we had V is out of the page. I guess V is that way. Okay, F equals 0. So the velocity and the field are in the same direction, so there is no magnetic interaction there. E. E, we had this. Boom, boom, boom. So this looks like we're in a field that's going into the page, and we have a negatively charged object, and we have a velocity like that. And all right, so I'm going to go V cross B, which B's into the page. So I'm going to go V, and it's into the page, cross B. So it would feel a force that way if it was positive, but it's not, it's negative. This is negative, so it's going to feel a force this way, right? Negative flips the sign, or the direction, which changes the direction. So, again, we got V down, cross with B into the page. So my thumb points that way, and it would feel a force that way if it was positive, but it's not positive, it's negative, so it's that way. F. We have all these field lines coming out of the page, and we have a positively charged object this time, and it's going kind of diagonally like that, and it's the velocity vector. All right, so here we go. I have V cross B, B's out of the page, V cross B, so that's going to feel a force this way. That's the direction of the force there. All right, so that is F. For each of the following, is the charged object positive, negative, positive or negative? Those are my only two choices. All right, so we got a B field like this. I'm drawing the B lines. They drew the vectors. They drew vectors at points in space. I'm just going to draw them as lines because it's quicker and easier. All right, so I have V. So F is into the page. So F is into the page. The force on this thing is into the page. So I have a velocity this way, and a velocity this way, and the magnetic field is this way. So if that was positive, V cross B is like that, it would be out of the page, but F is into the page, so this is negative. That's negative. So A, that is a negatively charged object because the force is out of the page. V cross B would give me out of the page, but this was into the page. So force is in the page. All right, so that was A. B. Oh, and they gave us a force vector is this way. This is the force vector. And V is into the page. So V's into the page. All right. And there's our B field. This is our B field. B is down. All right. So V is into the page. V cross B. V is into the page. B is down. So if it's positive, it would feel a force to the left, and it does feel a force to the left. So it is positive. C looks like this. Boom, 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 boom. C looks like that. And we have an object with a force this way. And a velocity this way. All right. So V cross B is this way. So this must be negative because the force is in the opposite direction. It's a negative. Oh, that's negative. Right? V cross B, B's into the page. We'd feel a force that way. But since it feels a force that way, that must be negative. V cross B, force that. This is positive. V cross B gives me a force that way, and the force is that way, therefore this is positive. So there you go. All right, I'm going to stop right there. I flipped over to the next problems. They get significantly more difficult. But anyways, that's the end of that. Hopefully you're getting the hang of this right-hand rule stuff. And catch you later.
Extreme Physics.